Hello, welcome to this tutorial for lessons 1 and 2 of predicate logic. Let's first recap what we have learned in these two lessons. We first encountered predicates. We know the predicate is the statement that contains variables named predicate variables. So the predicate instantiated is the proposition, and we know the predicate is usually more general than proposition, and it is more expressive. And we define the domain of predicate variables as the collection of all possible values that the variable may take. We should keep in mind that, in general, the predicate of multiple variables is not commutative. And then we learn the quantification, the universal and the existential quantifications. And a universal quantification is a quantifier, meaning given any or for all. And we use this sample. And this symbolic statement is equivalent to this P of x is true for every x in D. And we learn an existential quantification is a quantifier, meaning there is at least one or for all. And we use this example. And this existential quantification is equivalent to, say, P of x is true for at least one x in D. So in stock, we have these symbols for help us to express some quantified statement. And we have nested quantifications. So a proposition may contain multiple quantifiers. So the order of nesting matters, especially when the quantifiers are not the same. So in general, this left-hand side statement is not equivalent to this right-hand side, because in left-hand side, we know this y can vary with this x, and in the right-hand side, this y is fixed, but x is varied. Then we learn the negation of quantification. We know the negation of a universal quantification becomes the existential quantification, in where we take negation for every instantiation of the predicate. And the negation of an existential quantification becomes a universal quantification. And then we learn how to determine the truth values of some statements using three methods: the methods of exhaustion, the methods of case, the methods of logical derivation. And when the domain is not too big, we can use the exhaustion. And usually we can use the methods of case. And we can take negative example, that is the counter example, to disprove universal quantification. And we can use positive example to prove existential quantification. We should keep in mind that the negative example is not disproof of existential quantification, and positive example is not a proof of universal quantification, because for this universal quantification, this for all x in D P of x, it is equivalent to this conjunction of all instantiation of these predicates. So it is true when P of x is true for every x in D, and it is false as long as there exists one x in D. This instantiation is false. And for this existential quantification, we know this equivalent to the disconjunction of all the instantation. So it is true as long as one of these x in D such that this instantation is true, and it is false for when every x in D make these instantations false. So we learn the conditional quantification. So for every instantation of x, this is P of x implies Q of x is a conditional proposition. So we have some related quantifications. This contrapositive of the conditional quantification is this, and the converse and the inverse. We know that a conditional quantification is logically equivalent to its contrapositive. Now let's look into the exercise and say how to use what we have learned to solve questions. So the first question is to let us express some English statements using some symbolic logic. Consider predicates M of xy means x has sent an email to y, and predicate T of xy means x has called y. In this predicate, the variables x, y takes values in domain D, students in the class. So in the first sub-question, we suppose this sub-sentence contains the predicate variables and quantifiers. There exist at least 2 students in the class, so we need 2 predicate variables. And there are translate to there exists x in D, there exists y in D. And because there are 2 students and x should not equals y. And then we suppose there is 2 predicates. One is one student has sent the other an email. So by substitution, we know it means x sent an email to y. So we translate to M of x, y in symbolic. And there is an and, which translate to the disconjunction of another predicate. The second student has called the first student, and the second student y has called x, and that is T of y x. So the final answer is there exists x in D, there exists y in D, x not equals y, M of xy, and T of y x. So in the second sub-question, we have predicate variables and quantifiers in this sub-sentence. So there are some students which translate into there exists x in D. And we suppose there is everyone, so we need another variable for all y in D. And the predicates who have emailed everyone. So we translate into x send email to y. So in symbolic, it is m of xy. So the final answer is there exists x in D such that for all y in D, m of xy. Because these two quantifiers are different, so note that the order of the quantifiers is important. So the target of question 1 is to identify a statement containing a predicate and use quantifiers to express a property about all and some. So let's say question 2. Let us express some symbolic statements by English sentence. So consider predicate P of xy means x is involved in cos y, and in which there are two predicate variables x, y. X takes values in the domain S, student. Y takes values in the domain D, courses. So for the first steps question, the predicate variables and quantifiers, there exists x in S, translate to there exists a student, and the predicate P of x MH1812 by substitution we get its x is involved in cos MH1812. So the final answer is there exists a student such that this student is involved in the course. That is equivalent to say some students involved in the course MH1812. In the second sub-question, the predicate variables and quantifiers, there exists y in D, translate into there exists a cause. And the predicate P of Cairo y, and by substitution we get Cairo is involved in the cause y. So the final answer, there exists a cause such that Cairo is involved in this cause. That's equivalent to say Cairo is involved in some cause, or Cairo is involved in at least one cause. So for the third question, the predicates, variables, and quantifiers, there exists x in S. So there exists a student. The predicate is a conjunction. So it translates into x is involved in cos MH1812 and CZ2002. So the final answer is there exists a student such that this student is involved in MH1812 and in CZ2002. That is equivalent to say some students is involved in both MH1812 and CZ2002. So for the fourth sub-question, we have three predicates variables. And for the first two, there exists x in S, there exists x prime in S, we translate to there exist two students. And the third, for all y in D, we translate to for all courses. And the predicate is a conjunction. The first translate to x and x prime are different, distinct to student. And this if and only if proposition is translated into x is involved in the course y, if and only if x prime is involved in the course y. So the final answer, there exist two students, x and x prime, such that For all causes, X is enrolled in the cause if and only if X prime is enrolled in the cause. That is equivalent to say there exist two students which are enrolled in exactly the same courses. So the target of question 2 is similar to the target of the first question. So for question 3, we need to determine the choose values for this symbolic statement. So consider the predicate P love X by Z means the product of X by Z equals 1, in which there have 3 predicate variables X, Y, Z. They are in real numbers and they are positive. So the first sub-question statement translates into for all positive real numbers X, Y, Z, the product equals 1. So we know this is false because we take X equals 1, Y equals 1. They are in the domain. Then whenever Z not equals 1 in the domain, for example, Z equals 1/2, the product not equals 1. So that is, the instantiation of this predicate is false. So this is a counterexample for this universal quantification. And for the second sub-question, this existential quantification translates into there exist positive real numbers X, Y, Z, the product equals 1. We know this is true. We can take X equals 1, Y and Z both take equals 1, then the product equals 1. So this is a positive example for this existential quantification. And for the third sub-question, it translates into for all positive real numbers X and Y, there exists a real number, positive real number Z, such that the product equals 1. We know this is true because choose any positive real number X, Y, we can always find a positive real number. This Z equals 1 over XY, such that this predicate instantiation of this predicate is true. So this is a positive example for this existential quantification inside this universal quantification. So because for any positive X, Y, we can always find this positive example. So this is true. So for the fourth sub-question, this translates into there exists positive real number X for all Y, Z, the product equals 1. We know this is false because finding a single X such that the product equals 1, no matter what Y and Z, that is impossible. We can prove this by contradiction. So let's assume there exists such X. Then we know by assumption for any positive real number y1, z1, this predicate, the instantiation of these predicates, the products of x, y1, z1 equals 1, this is true. And also for positive real numbers y1 plus 1, z1, this instantiation of this predicate is also true. So for this second instantiation, we get x times y1 plus 1 times d1 equals 1 plus x d1. We know this x d1 is positive real number, so it's larger than 1. So we get this not equals 1. So we get a contradiction with the assumption. So this assumption does not hold. Therefore, this statement is false. So the target of the search question is to find truth value of a quantified statement. So let's say question 4. Let us express the negation of some quantified statement. So in the first sub-question, we say that there is a negation of two universal quantification. So let's denote the inner universal quantification by a predicate Q of x. And we know the negation of a universal quantification is an existential quantification, and we should take negation for this predicate. So we translate this into this form. Then we repeat this by use the same rule to the next negation. We get the negation of two universal quantification is equivalent to two existential quantification. And in the second sub-question, we take negation of two existential quantification. So again, let's denote the inner existential quantification by this predicate Q of x. And we know the negation of existential quantification is universal quantification. So we get this first immediate result, and then we iterate use the same rule on the next negation. We get the negation of two existential quantification is equivalent to two universal quantification. So the target of question 4 is to express the negation of a quantified statement. So let's say question 5 is to form the negation of some statement. So in the first sub-question, the negation of this existential quantification. So we translate into universal quantification, and we take negation to this inside proposition. And we know there is negation of a conjunction. So by the Morgan law, we take negation inside the bracket and get the disconjunction of two negation. So this is the result for the first question. For the second, we say there are several quantifications. And first, there is negation of an existential quantification. It translates into universal quantification. Again, negation existential translate to universal, and negation universal translate to existential. So we get the negation of this proposition. So we say there is negation of conjunction. By the Morgan law, we can take negation inside the brackets and get the disconjunction of two negation. And continue. And by definition, the negation of not equal is equivalent to x equals y. And by definition of this if and only if proposition, we know it is the conjunction of two conditional propositions. So because there is a negation of conjunction, we take negation inside brackets according to the Morgan law, and then we say there are two conditional propositions, and by the conversion theorem, we translate it into the negation and disconjunction form. And because there is negation and disconjunction, negation, disconjunction, by the Morgan law, we get the negation of the conjunction to conjunction. So here we also use the double negation equivalence and continue. We take the first atom as a whole, and there is a disconjunction and conjunction. So by distributivity, we take this disconjunction inside this bracket and get a conjunction of two disconjunction. And within these two disconjunction, we have conjunction, disconjunction. And again, by distributivity, we take this disconjunction inside this bracket and get the conjunction of two disconjunction. This is for the first disconjunction. This is for the second disconjunction. So in this first, both there is a negation of P or P. We know this is a tautology, and here P or negation of P. We know this is tautology, so we translate it into something and true, true and something, so it's equivalent to this form. So the negation of this statement is equivalent to this. So because there are several steps involved, we can check the sanity. In the intermediate step, we get this result. We know this is obvious, and for this is a negation of an if and only if proposition. So it is true when this if and only if proposition is false. So it's false when P of xj take different values to P of yz. So let's say or a form. So in this, we know when P of xj takes the same value with P of yz, so they are the same, we get P and not P. So it will get a contradiction. So whenever P of xj takes the same value with P of yz, this is false. This is consistent with this, so this makes sense. So the target of question 5 is to express the negation of quantified statements and manipulate quantified conditional statements. So let's say question 6. Show that this universal conditional composition is equivalent to its contrapositive. So we know for every instance of x, this P of x implies Q of x is a conditional proposition. Thus, we translate this conditional proposition to the form of negation and disconjunction. So this is according to the conversion theorem. Then we use the commutativity of this disconjunction, swap these two atoms. And to get the negation sample, we use the double negation. And then we can translate this negation, this conjunction form, use the conversion theorem to this error form. So this is the control positive of this conditional proposition. So they are equivalent. So the target of question 6 is to manipulate quantified conditional statements. So question 7, this is exactly what we have learned in the lecture video. So it's take negation of a universal conditional proposition. So the negation of universal is equivalent to the existential quantification. So we take negation to the inside proposition. Then this conditional proposition can translate to the negation and disconjunction form, use the conversion theorem. And then we have negation, disconjunction, and according to the Morgan law, we get the conjunction of two negation. And by the double negation, we cancel this double negation. So we get the results. So the target of section 7 is the same as section 6. So by now, we should be able to identify a statement containing a predicate and use quantifiers exist to express all there exists or some, etc. and express the negation of the universal quantification and the negation of existential quantification, and to determine the truth values of quantified statements and manipulate quantified conditional statements. So that is all for this tutorial. Hope you enjoy it.